No humanoid robot in the world is as sophisticated as Optimus, and Tesla owns components that no other company has. Elon Musk emphasized the superiority of Optimus, especially the Gen 3 version, which is being upgraded with over 100 integrated motors and sensors, capable of performing complex ballet movements and preparing for mass production. What final upgrades is Tesla completing for the Optimus? Before we begin, please help us reach 8,000 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Model Q, Tesla EVs, and the latest news. How has Tesla Bot Gen 3 truly mastered flexible movement? Watch how Optimus demonstrates astonishing agility from energetic shuffle dance moves to smooth ballet-like steps. What's impressive is its fluid turning, confident movement, and high precision, making it hard to believe this is a robot. Notably, the lead engineer of Tesla Bot confirmed that all these movements are performed in real time, without any CGI effects. Tesla has invested heavily in Optimus development and is accelerating progress to commercialize the robot early next year. However, not everyone is enthusiastic while many are captivated by Optimus's performance. Some remain skeptical about the practicality and application of this technology. So, how did Tesla train Optimus to perform such dance moves, and why are some viewers still not fully convinced? Rewind to 2021 when Elon Musk first introduced the humanoid robot concept. There was no actual prototype. Instead, a person in a robot suit humorously performed dance moves on stage. Although purely for entertainment, this moment created a strong first impression and helped define Tesla's bold media style. It was not until late 2023 that Optimus truly appeared with its first dance moves in a video unveiling Gen 2. Another notable moment came in October that year during the launch of Tesla's autonomous taxi network, when 43 Optimus robots appeared, and 5 performed an astonishing synchronized dance. This was the first time audiences saw Optimus dance live, making Tesla's robot the center of attention that night. Undeniably, Elon Musk, for his somewhat clumsy but humorous dancing, has inspired the Tesla team's unique style. In the latest update, Tesla released 2 videos of Optimus. Especially in the clip shared by Elon Musk on May 13th, Optimus showed powerful leg control with precise kicks, good balance, and no signs of losing control. However, a small detail caught online attention: a cable connected to the back of the robot. This raised doubts about whether Optimus was being assisted during the performance. In response, Milan Kovac, the lead Tesla bot engineer, quickly clarified that the cable does not hold the robot upright or assist movement. It serves only as a safety measure in case of falls. This means Optimus can stand and move independently without external support. From a humorous idea on stage, Optimus has made remarkable progress to become a humanoid robot capable of smooth movement, dancing, and natural balance. This rapid transformation shows Tesla's great ambition in robotics. And, with what has been demonstrated, Optimus is no longer science fiction, but becoming reality. In the videos, Optimus is not supported by cables while moving. The harness is solely for safety if the robot loses balance and falls. The real purpose of the video is to prove Optimus can maintain balance while dancing without any support devices. Tesla later released a second 42-second video titled "Just Getting Warmed Up," where Optimus performs ballet and modern dance moves with unprecedented flexibility and smoothness, completely free of tethering. Elon Musk also confirmed that Optimus will eventually be able to perform ballet dances as gracefully as professional dancers. Milan Kovac provided more important technical details about these videos. He stated that all Optimus movements occur in real time without time-lapse or remote control. This means the dance moves are processed and executed fully autonomously, reflecting low-latency control and data processing, key factors for deploying robots in real scenarios. Remarkably, all dance training was done in simulation environments and then transferred directly to the real robot without additional physical world training. This method, called zero-shot transfer, allows the robot to learn and repeat behaviors effectively without real-world practice. Thanks to virtual simulation, Optimus can train thousands of times faster than real-world training, speeding development while ensuring safety and reducing costs. This success is a major step toward closing the gap between simulation and real-world application, previously a top challenge in robotics. To achieve high adaptability in various environments, Tesla applied domain randomization, randomly changing simulation factors like slipperiness, surface friction, and robot body mass. This lets Optimus learn to adjust its movements to different real-world situations. Many may see these performances as mere demonstrations, but these dance improvements play a critical role in enhancing balance and stability when walking on varied terrains. This is especially significant if Tesla wants to commercialize Optimus for complex living and working environments. The development team even humorously responded to earlier jokes that Optimus walks like Biden, with the new version's light and graceful dance steps. More importantly, the performances clearly show Optimus's full-body coordination from shoulder and hip movements to bending and rotating its torso. These motions form the foundation for future tasks such as household assistance, elder care, or working in tight spaces. During testing, Milan Kovac also revealed Tesla is still adjusting hardware components like joint durability, motor strength, and cooling systems to ensure long-term stable operation. While robots don't get tired like humans, optimizing energy consumption is still necessary to avoid rapid battery drain or electrical overload. Therefore, these dance moves symbolize not only software progress, but also Tesla's long-term goal, developing a humanoid robot that can operate efficiently and flexibly in the real world. Once again, please help us reach 8,000 subscribers. This is important for us to stay motivated. Thank you. How has Tesla perfected the precision of the Tesla Optimus Gen 3 hand? When it comes to flexibility and dexterity, the human hand remains one of nature's most remarkable engineering marvels. With soft, elastic skin, agile fingers, and a highly mobile wrist, our hands can grasp, manipulate, and interact with objects of virtually any shape or texture with ease and precision. Replicating this level of biomechanical sophistication in robotics has long been considered one of the most formidable challenges in the field of humanoid design until now. A newly published patent from Tesla reveals a sophisticated system and method for constructing robotic hands and cable-driven fingers, engineered to closely emulate the anatomical structure and motion patterns of the human hand. This could mark a significant leap forward for Tesla's humanoid robot, Optimus, potentially allowing it to handle real-world objects and perform practical tasks with unprecedented finesse. According to Elon Musk, Tesla is planning to release a significantly upgraded version of Optimus by the end of this year, featuring a new robotic hand with 22 degrees of freedom, double the dexterity of the current version. The actuators will move almost entirely into the forearm, just like how the human arm works, Musk said, highlighting Tesla's ambition to mimic not just the shape of the human arm, but its underlying mechanics as well. At the heart of Tesla's innovation lies its under-actuated cable-driven architecture. Traditional robotic hands often use a dedicated actuator for each joint, which dramatically increases mechanical complexity, weight, and power consumption. Tesla's approach radically simplifies this with only 6 actuators in total, 2 for the thumb and 1 for each of the other fingers. This under-actuated strategy reduces the mechanical burden while maintaining a surprisingly natural range of motion. The fingers flex and extend not through rigid joint-by-joint control, but via a network of tensile cables that mimic the tendons in human hands. These cables are routed not around pivot points as in most traditional designs, but along the front face of the phalangeal bones, which enhances mechanical efficiency and allows for smoother, more human-like motion. Moreover, Tesla integrates torsional springs at the joints to provide passive stability and elasticity, ensuring that the fingers return to a neutral position when not actuated. The ends of the cables are also cleverly terminated inside the fingertips, eliminating unnecessary slack or mechanical constraint. Combined with magnetic position sensors for fine-grained finger tracking, Tesla's design offers a high level of precision and responsiveness, essential for delicate manipulation tasks. What makes Tesla's hand architecture particularly powerful is its modularity. The same foundational mechanism, cable-based under-actuation, can scale from simple 3-finger grippers used in industrial applications to highly articulated 5-finger hands designed for complex, humanoid tasks. This modularity is crucial for mass production, enabling Tesla to deploy variations of the technology across a wide range of use cases without redesigning the system from scratch each time. The decision to move most of the actuators into the forearm, just like in a real human, is more than a cosmetic choice. This shift allows the fingers themselves to remain light and fast-moving, reducing inertia and enabling more lifelike reflexes. It's a biologically inspired design choice that could unlock new levels of control and finesse, potentially allowing Optimus to tie shoelaces, fold clothes, prepare meals, or interact with fragile objects without causing damage. Tesla's progress in robotic hardware is tightly interwoven with its advancements in artificial intelligence. Just as full self-driving, FSD, relies on end-to-end neural networks trained on massive datasets, so too does Optimus benefit from Tesla's AI capabilities. The robot's hand is not merely a mechanical tool, it's part of a larger sensory motor system, powered by Tesla's custom-built FSD chips and real-time AI inference models. This synergy means that the robot doesn't just follow programmed motions, but can learn from data, adapt its grip dynamically, and respond to unexpected changes in its environment, key attributes for performing in real-world, unstructured settings. In essence, Tesla is bringing the same data-driven approach that revolutionized its vehicles to the domain of human-equivalent robotics. How is Elon Musk shaping the future of Tesla and Optimus? Elon Musk believes that if Tesla succeeds in both humanoid robots like Optimus and full self-driving technology, the company will no longer be limited to just an electric car manufacturer. Instead, Tesla will rise to become a global automation empire powered by artificial intelligence and robotics. In Musk's view, this is the path for Tesla to become the most valuable company on Earth. He often emphasizes that continuous improvement is what makes a company worth investing in. Musk cites Warren Buffett's analogy of the stock market as a man who shouts a price for your house every day, sometimes rational, sometimes not. But the actual value of the house never changes. Through this, he stresses that stock prices do not accurately reflect real progress, and that long-term value creation is what truly matters. While he admits short-term predictions are difficult, Musk remains confident in Tesla's potential over the next 3 to 5 years. At the core of his vision lies the rapid advancement of key technologies: the Optimus robot, artificial intelligence, and Tesla's massive gigacasting machines. These technologies not only help lower production costs, but also enable Tesla to scale globally at unprecedented speed. For Musk, this is not just technological progress, it's a fundamental transformation in how human labor and value are created. In his recent talks, Musk declared that Optimus could become Tesla's most important product, even surpassing electric vehicles in the clean energy ecosystem. Optimus is not merely a technical milestone, it embodies a broader humanitarian vision, liberating people from heavy, dangerous, and repetitive labor. Tesla's mission is expanding. Initially focused on reducing greenhouse gas emissions and promoting renewable energy, the company is now evolving toward a new objective: building a society where energy production and labor are abundant, efficient, and sustainable without harming the natural environment. Musk envisions a future where robots like Optimus work in factories, transport goods, or even care for the elderly. As these robots take over manual labor, humans will have more time to focus on creativity, education, and fields requiring emotional, ethical, or artistic intelligence.
They can walk around, they can interact. I think we're headed to a radically different world. I think a good world, an interesting world.
Elon Musk envisions a future where Tesla Bot becomes a daily companion. However, with a current response time still slow at 200 to 500 milliseconds and only 10,000 prototype robots produced, significant technical challenges remain. How will Tesla fix these issues to make Optimus run smoother? Before we begin, please help us reach 8,000 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Model Q, Tesla EVs, and the latest news. AI lacks sufficient training data. One of the most significant challenges Tesla Bot, also known as Optimus, faces is its AI brain. Despite inheriting Tesla's powerful full self-driving chip, controlling a humanoid robot is an entirely different endeavor. While autonomous vehicles primarily navigate flat roads using cameras and sensors, a humanoid robot must live in a three-dimensional space where variables can change unpredictably, from floor inclinations, slipperiness, lighting variations, to human interactions. Currently, Optimus is primarily trained in simulated environments within Tesla's factories, where conditions are stable and predictable. This training approach results in poor reflexes when the robot steps outside its comfort zone. A slightly inclined floor, an unexpected moving object, or a light bump from a human can cause Optimus to stumble. Its current reaction time, ranging from 200 to 500 milliseconds, is sufficient for it to miss a beat and fall if it miscalculates a movement. Unlike vehicle processors that focus on object recognition and flat surface navigation, humanoid robots require chips optimized for kinematics, calculating joint movements, managing forces, moments, and inertia, all in real time. This necessitates processing complex matrices, continuously analyzing sensor data, and making instantaneous decisions. Although the current FSD chip excels in visual AI, it isn't fully equipped to handle these intricate motion algorithms. Tesla is striving to broaden Optimus's AI learning scope by increasing the number of robots operating in real-world factory settings. This strategy aims to gather more real-world data rather than relying solely on simulations. However, this approach requires time, extensive testing, and numerous failures. AI, much like humans, needs to stumble and err before learning to recover and respond more effectively. If AI is the brain, then data is its oxygen. Without diverse real-world data, the robot will react clumsily to unforeseen situations. While Tesla possesses hardware advantages and mass production capabilities, transitioning Optimus from factory floors to human living spaces demands breakthroughs in both AI training and specialized hardware design. The future of robotics hinges not only on computational power, but also on adaptability, swift reflexes, and understanding the chaotic, random world outside. To achieve this, Tesla's journey has just begun. It's a long road ahead, but if successful, Optimus could become an indispensable part of daily life, not because it's perfect, but because it learns and adapts like a human. Another often overlooked yet crucial factor is context. Humans don't just react to images or movements. We rely on context. We recognize a hand wave as a greeting, not a push. We decide to dodge or catch a rolling ball based on the situation. For robots, understanding such nuances is complex. They must not only recognize images but also comprehend intentions, predict subsequent actions, and respond appropriately. This is the area where Optimus is still learning, grasping human behaviors and their living environments. Notably, a robot's movement isn't akin to programming an industrial arm to repeat a single task. When Optimus holds a glass, climbs stairs, or avoids a suddenly falling object, each action demands flexibility, delicacy, and millimeter-level precision. These seemingly simple tasks pose complex challenges in robotics, involving numerous control algorithms, force sensors, system latency, and continuous decision-making capabilities. A minor misstep can lead to loss of balance, dropping objects, or endangering nearby humans. Tesla acknowledges this and is progressing towards learning from real-world experiences, allowing the robot to perform actual tasks, make real mistakes, and learn genuinely. This approach necessitates not only constantly updated software, but also adaptable hardware. Arms must be sensitive to force, knees should feel ground contact, and the entire system must operate harmoniously like a living organism. This transcends pure technical challenges, merging technology, biology, and machine learning. Despite its limitations, Optimus holds a significant advantage. It was developed within Tesla's ecosystem, where data, hardware, AI, and manufacturing are seamlessly integrated. Once the AI becomes intelligent enough to learn from millions of interactions, and the hardware becomes adaptable to every minor action, that's when this robot will truly step into the world. Therefore, instead of merely asking, When will robots be perfect? Perhaps we should ponder, can robots learn like humans, fail, and then progress? If the answer is yes, then Optimus is on the right path. It just needs more time, more lessons, and a bit more patience from us. The FSD Chip. The FSD chip developed by Tesla for self-driving cars with processing power of up to 144 TOPS is a remarkable achievement. But have you ever wondered whether that chip is truly suitable for a humanoid robot like the Tesla bot? A car only needs to recognize lane markings, traffic lights, and objects either stationary or moving across flat terrain. A robot, on the other hand, operates in a much more complex world where everything is in motion, unexpected, and demands near-instant reflexes. Can a chip designed to read streets really handle the flood of sensor data coming from cameras, IMUs, force sensors, audio inputs, and joint states all at the same time, with no delay or miscalculation? Because even a delay of a few hundred milliseconds could cause the robot to lose balance, trip, or react incorrectly to a human. Do you think a robot can move fast enough to avoid a child suddenly running toward it from the side without being pre-programmed for it? The core issue is that the FSD chip was never designed for kinematic calculations, the kind needed for a robot to coordinate its joints gracefully, control forces and torque, and maintain balance even when nudged or standing on a tilted surface. Imagine a robot carrying something when the floor beneath it subtly slopes. If its reflexes aren't fast and precise enough, what do you think will happen? And it's not just about performance. Power consumption is also a serious concern. The complex computations required, such as rotation matrices, inverse force calculations, and adjusting trajectories in 3D space, can drain power very quickly if the chip isn't optimized for that purpose. Can Tesla create a robot that's both intelligent and energy efficient enough to run for several hours straight without needing a recharge? The software can't just be copied from cars either. The control algorithms must be rewritten to accommodate complex 3D movement, not to mention the need to learn from real-world environments instead of simulations. Do you really believe a robot trained inside a factory with flat floors and stable lighting can immediately adapt to a cramped home with slippery wooden floors and kids running around? This is the crossroads Tesla finds itself at. They can continue to optimize existing technology and invest more seriously in a brand new hardware architecture purpose-built for robotics. A custom chip designed specifically to handle real-time motion and reflex processing is almost essential if they want Optimus to operate in the real world. So, what do you think? Will Tesla start from scratch and build a dedicated chip for robots? Or will they keep tweaking the current FSD chip to save time and cost? In this race, is speed more important than a solid foundation? And what truly determines whether Optimus can become a real companion in our daily lives? The answer remains unclear, but one thing is certain. If a robot is to understand, adapt, and respond like a human, the road ahead won't be easy. But precisely because of that, it's worth the wait. Sensors and cameras. The current Tesla bot uses a sensor system that includes cameras, force sensors on the hands and feet, as well as accelerometers and gyroscopes, IMUs. However, these components still have notable limitations in sensitivity and accuracy, directly impacting the robot's ability to perceive and interact effectively in real-world environments. Regarding its cameras, Tesla bot primarily relies on standard visual sensors with resolution and sensitivity that are not yet sufficient to distinguish small objects or function efficiently in low light conditions. This makes it difficult for the robot to handle complex tasks, such as picking up small items or navigating dimly lit areas, often leading to recognition errors and delayed reactions. In contrast, depth cameras like those used by Boston Dynamics allow robots to create three-dimensional spatial maps with accuracy up to 1 to 2 centimeters, enabling object recognition in complex environments that is 30 to 50% more precise than with conventional cameras. The IMU sensors currently equipped on Tesla bot exhibit a processing delay of about 30 milliseconds. While this may seem minimal, in a humanoid robot system that needs to respond instantly to maintain balance, such latency can lead to instability or wobbling, especially when navigating uneven terrain or reacting to external disturbances. Boston Dynamics uses IMUs with less than 10 milliseconds of delay, combined with advanced signal processing algorithms, enabling its Atlas robot to respond to balance disruptions up to 3 times faster than Tesla bot. As for the force sensors installed in the robot's hands and feet, Tesla bot currently employs sensors that fall short of the high precision found in those used by companies like Robotic or Shadow Robot, well known for their industrial robotics and dexterous robotic hands. Force sensors that lack sufficient sensitivity and accuracy hinder the robot's ability to perform delicate tasks, such as grasping fragile objects or interacting gently with humans. Robotic sensors can detect force with precision up to plus or minus 0.1 newtons, whereas Tesla bot's current sensors operate at around plus or minus 0.5 newtons, which significantly limits its capacity for fine manipulation. Figure A. I takes a multi-sensor approach, using 3 stereo cameras on the chest, 1 camera on the head, and highly sensitive proximity sensors around the waist. This setup allows the robot to detect and respond to obstacles in 3D space with high accuracy. Thanks to this integrated sensor system, Figure AI can react to moving objects in under 50 milliseconds, whereas Tesla bot still experiences latencies exceeding 100 milliseconds. Tesla bot's continued reliance on standard cameras and underdeveloped force sensors results in a lack of detailed perception and quick reaction capabilities in real-world environments. This not only limits operational efficiency, but also poses safety concerns when the robot interacts with humans or fragile objects, an essential factor in industrial and service applications. To improve its potential in sectors such as logistics, healthcare, and home assistance, Tesla must invest significantly in upgrading its sensor systems. This includes integrating technologies like LiDAR or advanced depth cameras, while also enhancing its force sensors and IMUs to reduce latency and increase sensitivity. Such upgrades would enable the robot to perform complex actions like picking up and holding small objects, balancing on uneven surfaces, and responding swiftly to unexpected situations in a smoother and safer manner. Motors play a pivotal role in the mobility and task execution of the Tesla bot. Elon Musk has emphasized a compact motor design with high torque, aiming to optimize weight and size to enhance the robot's agility. However, real-world testing has revealed that Optimus's motors suffer from significant overheating issues, with temperatures rising to 60 to 70 degrees Celsius after just 10 minutes of continuous operation. This heat not only reduces performance, but also affects the durability and stability of the motors, forcing the robot to lower its power output to avoid damage. This poses a major challenge for a robot that is expected to operate continuously and reliably in diverse environments. Furthermore, the Tesla bot's response speed and acceleration capabilities lag far behind those of its competitors. In demo videos, Optimus can only rotate its joints at about 30 degrees per second, more than half the speed of Boston Dynamics' Atlas, which is equipped with larger motors and advanced control systems. The rapid overheating and lack of optimization in motor control result in delayed reactions, limiting the robot's ability to perform complex and swift movements essential for humanoid functionality. Boston Dynamics serves as a prime example of how these technical challenges can be addressed. Their Atlas robot features an active cooling system that includes fans and heat sinks, allowing it to effectively manage motor temperature even during high-intensity, continuous operation. This system not only protects the motors from overheating, but also ensures that the robot maintains optimal performance. Additionally, Atlas employs highly sophisticated force control algorithms that distribute torque flexibly and precisely across each joint, enabling smooth, rapid, and stable movements. These technological advances help Boston Dynamics maintain its leading position in the humanoid robotics sector. We appreciate your contributions and hope you will have the most relaxing feelings after watching this video. If you did, please hit the like button and join the Techno Creator family by subscribing to our channel. And don't miss out on any of our awesome videos by hitting the bell icon. We value your feedback and your time. Thank you so much for watching, and we'll see you soon. Until then, stay safe and have fun.